Good day. This is the solution for sample problem number 10, the long problem. So I will first read the problem. The external force P is designed to cause the rotation of the rigid link BCD, in effect displacing the rigid switch E downwards and compressing the aluminum block F. The rigid link BCD is pinned at C and supported by the shear spring at B. The shear spring consists of two rubber pads sandwiching the steel bar AB. Determine the maximum permissible value of P in meganewtons given the following conditions. The shear stress in the pads should not exceed 13 megapascal. The normal stress along the x-axis for block F should not exceed 130 megapascals, and the expansion of block F along the z-axis is limited to 1.3 millimeters. Note that the expansion of block F along the x-axis is hindered by the rigid walls. Assume that for all deformable bodies, the strain is uniform at any value of P. So this is the figure for the problem. Again, there is an external force P applied on the rigid link BCD. So take note that the link BCD is rigid as well as the switch E. Those will not deform. Okay. The common mistake when this problem was given was as an exam. Firstly, the force P, the students assumed that the force in member AB is automatically P. So this is wrong. P is actually applied on BCD. Assuming that the member AB is subjected to the force P, or rather the normal force in member AB is P outright, neglects all the other structures that are connected to AB, like the rubber pads, and of course, since BCD is connected to the bar F and the switch E, it also neglects those forces as well as the pin. So do not assume that the normal force in AB is P. Okay? Also, one of the common mistakes in this problem was the students did not bother making the deformation diagram. Again, I will show you later why you need to draw the deformation diagram. Okay? So, take note from the problem statement for block F, there are rigid walls along the x-axis. So, the deformation along the x-axis is hindered by the rigid walls. Also, there are no mention of any walls along the z-axis. In fact, the deformation along the z-axis is limited to 1.3 millimeters. So we draw first the FBDs of the various members of the structure. First, we draw the FBD for link BCD. So of course, you have the external force P. And then, you will put a normal force for AB, FAB, and it would not be equal to P. Why? Because you still have your force in pin C, CX and CY. So, it would affect the value of FAB as well as your force in the bar F. Of course, the member in contact with BCD, automatically in contact with BCD, is the rigid switch E. But if you draw the diagram of E, it is just a two-force member. Therefore, the force felt by E would just be equal to the force felt by F along the y-axis. So again, if you equate FAB to P, then you would be neglecting the other forces on the link. Okay? So the only equation that we would be getting from this diagram is your summation of moment about the point C. So that would be FAB times 1. So remember from the figure that the distance of C to B is 1. Also, that is the distance from C to E. So FAB times 1 plus FE times 1 is equal to P times 1. We will not be summing forces along X and Y anymore, as it will just add up to our unknowns. Next, for member AB. So again, you have your FAB here. It's tensile. We assumed it to be tensile because the pulling force P would pull your link BCD to the right. So we assume that FAB will elongate. And then, of course, you have your rubber pads that are attached to your member AB. So that there are two rubber pads, one on top and one at the bottom. And this would now be the shear force on the rubber pads as well, those two forces. So with that, we would have summation of forces along X, FAB is equal to 2V. That would be our equation 2. And lastly, for the bar F, again, I will not be showing you the FBD of the switch E because it's just a two-force member and FE will just be equal to the force along Y for the bar F. Now, for the bar F, of course, you have your force along the Y-axis, FFY, and it would be countered by another FFY below because of the contact with the ground of your bar F. And then, since there are rigid walls preventing deformation along the x-axis, we would have to put a force. So, of course, the walls would be pushing kasi, diba, FFY, since FFY is compressive, the bar will thicken. The bar will be compressed, so the length would decrease, and then it would thicken along the x-axis. So the walls will prevent the elongation along the x-axis, hence your compressive force X. Now, we would not be able to make an equilibrium equation by summing forces or summing moment that would relate FFX to FFY, right? But we can relate these two forces by taking note that the total deformation or strain along the x-axis is 0 since the walls are hindering the deformation. So here, you have your strain along x equal to 0. So again, I use the convention that if the forces are compressive, I place negative on the values. So this is our equation of strain along x. We can remove E from the equation because the other side of the equation is 0 and E will just cancel out. So here, we replaced stress by force over area and nu equal to 0.4. So when we simplify, again, these values, the 100 and 500 and then the 50 and 100 came from the given. You can go back. And then when we simplify this equation, you have this equation number 3. F of x is equal to 4 times FF1. So now, in summary, from everything that we have done, the unknowns, we have 5 unknowns: FAB, P, FFY, V, and FFX. I did not include FE anymore since FE is just equal to FFY. And we have 3 equations there. So we have 5 unknowns. We only have 3 equations. Of course, we have our cases, right? We have the allowable stress in the rubber pads, allowable stress along the x-axis, and then the allowed deformation. Of course, they will give us values, but just one value per case. So we would still need another equation. And that's where your deformation diagram comes in. So how will the whole thing deform? So this is the figure. Of course, remember that BCD is rigid as well as E. So they will move, BCD and E will move, but they will not deform. So how will BCD move? Here. Of course, P is pulling point B to the right. Hence, your BCD, your linked BCD will rotate. Okay? Will rotate clockwise. Of course, it will not go down. The point C will not go down or go to or move horizontally because of the pin connection. But point B moved horizontally by small angle approximation, of course. And also point D moved vertically downwards. So the movement of point D vertically downwards equates to the deformation of F rather, along the y-axis because E is rigid. So it will not deform. So the downward movement of point D will just equate to the deformation of F along the y-axis. How about the movement of point B horizontally? So you have two deforming bodies here. You have the rubber pads and the member AB. Both are subjected to forces. So what will happen? So the rubber pads will be feeling shear stress. And so they would incur shear deformation. So the point A will move by this much, and that would equate to the deformation of the rubber pads, the shear deformation of the rubber pads. And then AB, which is subjected to a tensile force, will elongate. Hence, the movement of point B will be the sum of the deformation of the rubber pads and the deformation of AB. So to simplify, so this is the simplified version of our deformation diagram. So again, the movement of point B here to the new position is equal to the sum of the shear deformation of the rubber pads and the elongation of AB. Whereas the movement of point D to its new position is equal to the deformation or the compression of bar F along the y-axis because of the force along F. Now, this is the equation. Delta S plus AB is equal to delta Fy. Actually, this should be a similar triangles equation. So, this should have a denominator of 1. However, I did not include it kasi masisimplify din naman. Bakit siya similar triangles? So, take note na yung link BCD ay rigid. Therefore, kung mag-move man siya pa-clockwise o mag-rotate man siya pa-clockwise, yung angle between this line BC, and line CE is still 90 degrees. 90 degrees pa rin itong angle na to. Therefore, this angle and this angle are equal. So, equal yung angles na yan. Tapos, 90 degrees tong nasa taas. 90 degrees din to. Therefore, similar triangles sila kasi malamang mag-equal na rin yung third angle. So, similar triangles pa rin yung ginamit dito sa ganitong setup na equation. Nagkataon nga lang na parehong 1 yung length ni BC at saka ni CE. Okay? So, when we substitute the equations VL over AG, FPL over AE, sa equation na to, here's what will come about. And take note that the deformation along Y is equal to the strain along Y and the L naught. L naught is 500 millimeters. Yun nga lang, since the bar F is subjected to multi-axial loading, we have this equation for strain. Okay? So, again, you have a force along Y, this is your axial strain, and you have a force along X, that is your lateral strain. There's no force along the Z-axis because hindi naman sinabi sa problem na may hindrance sa movement along the Z-axis. Once we substitute the values, so here we have, yan, yung 20 millimeters, check nyo na lang, bakit yan yung length na ginamit for the rubber pads, and then PL over AE follows. So, yung E dito sa equation, nilipat ko na lang, pinactor out ko para hindi na masyadong fraction over fraction yung values. Now, I just want to emphasize kung bakit hindi ako naglagay ng negative sign dito kay FFY at kay FFX kahit na compressive naman yung force. Diba dapat pagka mag-multi-axial loading ka, tapos pag tension yung force, ipa-positive mo, pag compression yung force, negative mo. So, bakit hindi ko siya nilagyan ng negative sign? Tingnan nyo yung ating deformation diagram. Si delta Fy, pababa, compression siya. Siyempre, ang magko-contribute ng positive na value para sa magnitude na to ay yung compression na force. Kasi siya yung nagpaikse. Tapos, yung konting inihaba nung material dahil sa compressive force along the x-axis. Ito yon, may negative naman na sign dito. Kumbaga, parang ang nangyari talaga sa kanya, na-compress siya hanggang dito dahil sa FFY, tapos may bawi na tension dahil sa compressive force sa FFX. So, naging positive tuloy yung FFY, negative yung FFX. So, ganon. Kapag ang deformation equation nyo ay total deformation equal to something, may value or 0, tapos nag-add-add lang kayo, hindi kayo gumawa ng deformation diagram, pwede yun, dire-diretso gawin nyo yung positive, tension, negative compression. Pero kung manggagaling siya sa deformation diagram, tapos sa deformation diagram nyo, yung movement o yung pagkaka-deform ay compressive. Ang nangyayari, nagiging positive na yung compressive force ninyo. Tapos negative na yung tension. Kasi na-compress siya. Mas malaki yung naging compression kesa sa naging tension. Okay. So, ito na yung simplified na equation nung previous para mas madali natin siyang magamit. So, that would be your equation 4. Okay. So, again, summarizing, you have these equations, 5 unknowns, 4 equations. We can now proceed to the cases. Again, note na sa equation 4, you have to use Newton sa forces kasi nag-megapascal ako sa mga E. Okay? So here, case 1, you maximize the shear stress in the rubber pads. So, of course, shear stress is still V over A. This is the area of the rubber pads. You get V equal to 65 kilonewtons. And then use equation 2 to get FAB, equation 4 to get FFY, and equation 1 to get P. Next case, you maximize the stress along the x-axis of bar F. So, ganun pa rin naman yung formula natin ng stress. F over A pa rin siya. Area, 100 times 500. So, ito na, 6,500 kilonewton yung FFX. And so, you have equation 3. You use equation 3 to get FFY and equation 2 and 4 to equations 2 unknowns to get FAB and V. And as you can see, all of your values here in case 2 are less than case 1. And case 1 values exceed the values for case 2. Hence, case 1 already fails. And we get the P for case 2. 1,736.277 kilonewtons. Next, last case, case 3, you maximize the expansion of the block along the z-axis, 1.3 millimeters. So, dito, again, yung delta FC is equal to the initial length of FC times the strain of FC. But again, bar F is experiencing multi-axial loading. So, ganito yung magiging equation natin ng strain. For Z, Z is your lateral dimension. Bumalik ako dito sa paggamit ng negative for the compression. Pero kung multiply natin yan sa 0.4, sa negative, magpa-positive. Hence, mag-expand talaga yung material mo along the z-axis. Kasi nga, parang compressive force along the x and the y axis. So, here, ang nakuha nating FFY gamit nitong equation na to, plus equation 3, is 9,285.7 kilonewton. So, I don't need to push through with this solution kasi it already exceeds the 1,625 kilonewton that we were able to solve for case 2. Okay? So, case 2 na yung ating final na mag-govern na case. And so, your answer would be 1,736.277 kilonewtons. But, according sa problem, I was not able to note it earlier. The answer should be in meganewtons. So, therefore, the answer is 1.736 meganewtons. Thank you for watching.